The internet, the sea. Now, there's a challenge, and to fully understand the challenge, we need to go back over a century and a half. Let's begin. In October 1831, the English scientist Michael Faraday, famed a decade earlier for creating what was essentially the first battery, had discovered electromagnetic induction by first sliding a magnet through a coiled wire and then spinning a copper plate through a magnet. This Faraday disc created a continuous current which could flow down a wire, really the first electric generator. Soon after, and independently, both William Sturgeon in Britain and Joseph Henry in America discovered that by using electricity and reversing these methods, sending a current through a coiled wire, they could essentially create a strong electromagnet. The more coils you added, the stronger this magnet could be, and it didn't take long for Henry to realise that it could be operated at whim over a large distance, essentially a remote doorbell or even the telegraph. This was the age of steam, and so such technology was both miraculous and highly useful. Taking this lead, the William Cooke and Charles Wheatstone telegraph was implemented in 1937 as a method to communicate between Euston and Camden town stations. This early system used a board configured with needles which could be moved to point towards letters of the alphabet depending on the magnetism applied across the lines. But combined with Samuel Morse's messaging system, conjured in the 1840s, suddenly we had the ability to communicate over huge distances with a simple, serial and unified code. In August 1850, John Watkins Brett's English Channel Submarine Telegraph Company, bit of a mouthful, laid the first line to cross the English Channel using a tugboat named Goliath. This early test used a copper wire coated in gutta percha, a latex-like tree sap from the Palaquium gutta tree. However, this initial protection was simply inadequate. In September 1851, a new cable with a thicker and bound layer of protection around the core was laid, proving much more successful. It didn't take long for entrepreneurs to realise that it would be incredibly useful and profitable to connect the two largest powers on Earth, Britain and America, using this powerful system. In fact, it was Samuel Morse himself who postulated it may be possible. Around the same time, US Navy officer and astronomer Lieutenant Matthew Maury had recently finished a series of depth soundings across the Atlantic. This was usually by simply dragging a weight across the ocean floor to measure the distance. His findings revealed a 2,000-mile sedimented plateau between Newfoundland and Ireland which avoided the extreme depths which would make cable laying impossible. This miraculous stroke of luck was what American Cyrus Field and Englishmen John Watkins Brett and Charles Tilston Bright needed to hear, and by 1857 the Atlantic Telegraph Company was formed with £350,000 of secured capital. The company board consisted of 18 UK members, 9 from the US and 3 from Canada, and with that, one of the largest projects undertaken by man had begun. On the first of several attempts, and using a huge ship filled with coiled cable, they simply tried to reel the heavy lumbering line from one side to the other. But despite several attempts, they kept snapping under the load. Finally, on the 29th of July 1858, two parts of a cable were spliced together in the mid-Atlantic and each was taken in opposite directions. One to Newfoundland on the USS Niagara, the other to Southwest Ireland on the HMS Agamemnon. Both ships supplied thanks to government cooperation. Now, looking at these ships, you wouldn't really associate them with this new age of instant communication dawning, but regardless, just 6 days later, the link was established. Not only was this an incredible achievement, but it also beat off competition from the likes of Western Union, who were trying to push the idea of going the opposite way around the globe, connecting the shorter sea distance but larger land distance between Alaska and Siberia and then onto Europe. Queen Victoria was the first to use this incredible new communication cable, sending a message of congratulations to President Buchanan almost immediately. However, celebrations didn't last long. Captured using a siphon recorder at Newfoundland, this initial message took an incredible 16 hours to send. The signal was simply just too weak. Under the illusion that electricity flowed like water rather than pulses, as we knew shortly after, British engineer Wildman Whitehouse tried to force a higher voltage down the line to force the messages through. This just fried the cable and it stopped working entirely. The problem was, these pulses were simply getting distorted, travelling across the huge length of metal. So with careful studying and contemplation, engineers and scientists made improvements to the composition, design, armouring and laying of the cable, including twisting layers of iron strands around for increased armour and the use of a pure copper core as suggested by Belfast scientist Lord Kelvin. The huge hulking sailing ship Great Eastern, using an also improved laying method, was put to the task of unreeling the massive 9,000 tons of cable out across the ocean floor. Despite a failed first attempt with suspected threat of sabotage on board and losing the cable end on more than one occasion, the task was finally completed, and on Friday the 27th of July 1866, the first clear message was sent from Ireland to Newfoundland. A treaty of peace has been signed between Austria and Prussia. With one message, the world had become significantly smaller, although the rate of transmission was still just a few words per hour, using good old Morse code. And actually, it was Samuel Morse himself who had predicted and arguably seeded this idea way back in 1843. Importantly, and despite its numerous hiccups, the project was also a financial success. Compared to traditional slow methods of communication by sea, taking at least 2 weeks, communications sent by the British government to commanders in Canada alone saved over £50,000 in little time at all. This paved the way for further private investment. The world was becoming connected, and there was no going back. In 1866, the price of sending a telegram down the cable was $1.25 per word. That's over $20 per word in today's money. It certainly wasn't cheap, but still far cheaper than sending a note on a boat. Because of this, by the early 1900s there were over a dozen transatlantic cables, each of which performing admirably. This was helped by improvements in understanding, including that bandwidth of a cable is hindered by an imbalance between capacitive and inductive reactance, causing electrical resonance and signal distortion. The progress on these lines ensured there were hardly any outages from 1866 onwards, but over those 40-odd years the world had begun to move on. Although many minds laid the foundations for the telephone, including a patent battle with Elisha Gray, it is commonly accepted that Alexander Bell's harmonic telegraph, which could send several pitches down a line simultaneously, is the real dawn of the modern phone line. Across the world, existing land telegraph cables were repurposed to transmit voices rather than beeps. This is something the transatlantic cables would have to adapt to. So, although a telegraph consists purely of strong binary electrical pulses, the new telephone call was made up of a complex electrical wave, which would simply get lost across the great lengths of undersea cable. What came out the other end would be simply too weak to discern or even notice. So to get a voice from one side to the other, a new marvel would be needed: the amplifier. Sir John Ambrose Fleming would invent the first vacuum tube in 1904, the diode, really an incandescent bulb with an extra electrode inside called an anode. This had the ability to convert AC signals into DC by restricting flow of current from the hot filament or cathode to the anode. But in 1906 it would be Lee De Forest who would turn this into a practical amplification device with the Audion, the first triode vacuum tube. Introducing a new electrode in the form of a grid, a small amount of positive charge could be applied to it, which would in turn amplify the charge coming from the cathode to the anode whilst retaining the same waveform. Although telegraph amplification wasn't new, in fact, electromagnetic relays had been used to increase signal strength over land telegraph by essentially receiving and then repeating the signal, these devices couldn't handle the complex waveform required for voice transmission. They also weren't used for undersea cables due to the complexity of installing and powering such devices underwater. By 1912, AT&T had developed the triode into a practical amplifier, which allowed the first transcontinental telephone line to open in 1915, connecting the east and west coasts of the United States. However, despite telephone calls being made on shorter undersea cables where amplification wasn't necessary, the technology was still not portable or practical enough to install under oceans like the Atlantic and open up larger scale telephone communications. To make matters worse for the undersea cable business, the development of the amplifier also enabled radio signal to extend its reach over great distances. Undersea cables hadn't stood still, mind. Multiplexing had been introduced, allowing multiple messages to be sent at 120 words per minute. But even so, the 1920s saw radio communication taking the front seat. It was faster and cheaper than our trusty lines of metal, not forgetting that those metal lines also needed repair. If a shark was to bite it or a trawler was to cut through the line, then measuring equipment would need to be used to find where the break was, before zigzagging across the line to literally grapple it up from the ocean floor for re-splicing. In 1927, the radio telephone service initially allowed one telephone call at a time between the United Kingdom and the United States. A queue system was implemented, and when it was your time, the operator would call you back up to connect to your transatlantic destination. Over the coming years, the capacity would of course increase, but radio was still at the mercy of the weather and atmospheric conditions, proving pretty unreliable. A better and also more secure system was needed. It wouldn't be until the 1950s that the vacuum tube amplifier was perfected for undersea use, some of the most reliable vacuum amplifiers ever made. These amplifiers had to be spliced into the cable every 20 miles, meaning 200 amplification tubes were required for 2,000 miles of cable. In 1955, AT&T and the British Post Office would begin the process of once again laying two undersea cables, this time for telephone communication. One cable would handle the west to east portion of the conversation, whilst the other the east to west. Each cable took a year to lay between Galnock Bay, Scotland and our faithful Newfoundland, but having learned from the experiences of cable laying almost a century prior, this time things went without a hitch. We also had new technologies. Sonar could be deployed to find new routes undersea for cable to be laid, and to avoid those pesky fishing vessels from ripping lines up, cables could even be buried in the most risky parts using an underwater machine which created a groove at the front for the cable to fall into. Transatlantic 1, or TAT-1, was ready for operation on September 25, 1956. With AT&T Chairman Cleo Craig calling Postmaster General Dr. Charles Hill to celebrate the momentous occasion.
This is Dr. Hill in London. Is that you, Mr. Craig?
This is Mr. Craig.
Well, it's very good to hear your voice.
The lines could carry 36 telephone conversations at a time, with initial costs set at £1 per minute, equivalent to about £24 or $31 a minute today. A call would soon add up, but despite that, demand increased rapidly, again requiring a queue system like the telegraph line of old.
Each of these tickets is a demand for a telephone call from England to the continent.
Technology advancements such as time assignment speech interpolation meant by 1960 the cables could carry twice as many calls. But just around the corner, in 1976, new lines were added, including TAT6, which used transistors for amplification and could handle 4,000 telephone channels simultaneously. TAT1 was retired in 1978, and it seemed like we had all the capacity we'd ever need. But we were wrong. The next issue were mobile phones. Just like the radio communication of the 1920s, the world had become wireless, and with satellites becoming cheaper, it seemed once again that cable would become a buried relic. Well, actually, satellite communication had been around since the 60s, but the delays caused by sending data from the phone to the transmitter, up to a satellite in geostationary orbit, back to a receiver, and then back to the end phone meant that conversing was usually unnatural, staggered, and lacking the nuances and cues brought by almost instantaneous connections. But mobile phones did mean more lines, more people talking, and the need for greater international bandwidth. Thankfully, 1988 saw the introduction of TAT8, the first fibre optic transatlantic cable, providing a transfer rate of 280 megabits per second, equivalent to a whopping 40,000 telephone channels.
Today, we're no longer just a phone company or just a telephone network. We're an international communications company.
1992 would see TAT9, which doubled that capacity, and also the introduction of TAT10, which could handle over 1,000 megabits per second. Yes, whilst up to now we measured cable capacity in number of lines, now we're switching to data. This is because, rather than analog, fibre optic is a digital transmission method. That's not to say that copper wires can't carry digital data, it's just that fibre optic is very much suited for it. So here's the crack. Optical fibre is a glass tube, usually made of pure silicon dioxide, but with a component of boron or germanium to decrease its index of refraction. This means that when you shine a light from one end of the fibre, the light is reflected entirely within the strand and out the other end. TAT8 contained just 6 of these optical fibres, 3 pairs for each direction, although one pair was purely for backup purposes. These were suspended in elastomer and protected by steel wire with an outer copper cylinder. The cable was less than an inch in diameter, but its carrying capacity was far higher than anything prior. The cable was laid between Tuckerton, New Jersey and Weymouth, England. By shining a specific intensity of laser down this fibre to indicate 0 and another intensity to indicate 1, these binary signals could move at the speed of light, making communication almost instantaneous. You might think that because the light is completely contained within the strand, there is no use for a repeater or an amplifier, but in fact there still is. The light actually attenuates as it travels for huge distances, and so amplifiers are required every 60 miles or so to repeat the signal. These were powered by a high voltage direct current passed through a conductor at the cable's centre. To convert an analog phone signal, which made up the majority of traffic then, engineers used pulse code modulation to convert the wave into a digital approximation. Of course, do this fast enough and suddenly we can fit thousands of phone conversations down a single strand. Of course, being the early to mid-90s, this was also the dawn of the World Wide Web, so what better means of communication to have than fibre optic cables connecting the world? Initially, we connected to this modern wonder with modems, an analog method of communicating with our ISP, where digital signals were modulated into an analog signal and then back again at the other end. It may be strange thinking about connecting a computer in the UK with an ISP or bulletin board in the US via a modem, especially when you consider this analog signal was very possibly converted again and sent down a fibre optic cable, but it wouldn't take long for the world to catch up and for digital connections to connect directly from computer to computer, both via land fibre optics and more widely making use of specific frequencies to unlock extra capacity and enable DSL connections down standard copper phone wires. From this point, fibre optic cables became more and more the main method for sending data across the sea. Currently, 99% of data traffic is sent using undersea cables, with satellites accounting for a single percent. The faster transmission and increased carrying capacity and security completely outmodes what satellites can offer, and it's clear that investment into these huge lines will continue into the future. Since the 90s, fibre optic undersea cables have improved significantly. This includes the use of wavelength division multiplexing, which essentially allows different colours of laser to be sent simultaneously, therefore increasing bandwidth. They also have redundancy, usually by being laid as a ring network. This means if one part snaps or breaks, data can still travel to the destination using the longer route. Modern fibre optic undersea cables, whether traversing the Atlantic or Pacific Ocean, can carry multiple terabits per second, a trillion-fold increase in carrying capacity in less than 200 years. And when you think about it, that's not too shabby at all. Really, it's all thanks to those pioneers back in the 19th century who had a vision and made it happen. Of course, we still need those huge hulking ships to painstakingly lay all the cables, but now we have ships completely dedicated to the task, and they're not driven by paddles or wind or even coal, which is nice. I guess some things just move along faster than others.